Hi, everyone. Welcome to the Learning Curve, Scale AI's monthly Tech Talk series. Today's topic is scale mapping. Before we begin, just a few housekeeping notes. This webinar is being recorded, and we will send the recording via email. We will have a Q&A after the presentation, but if you have any questions as we go through the presentation, please submit them using the Q&A feature in the Zoom. Lastly, we will be sending a survey in the Zoom chat. Please complete it post-webinar. Our speakers today include Elliot Branson, who is a Director of Engineering at Scale, where he leads the machine learning, 3D, and platform teams, as well as the development of new products such as Nucleus and mapping. Marja Kobo is a Product Manager at Scale, where she leads the mapping and design teams. And Stephen Howe is a Software Engineer at Scale, where he leads the technical development of mapping. And with that, Elliot, please go ahead and take it away.
Awesome. Thank you so much. So Maria and Stephen are going to go into kind of a bit about why you should care about mapping and how we're technically tackling the problem of mapping here at Scale. But I want to start out and talk about why you should care about Scale's maps at all. So Scale pioneered annotating complex 3D sensor data for self-driving cars. We did this by not running away from challenging problems that people brought to us. And 5 years ago, when the company was founded, the idea of annotating or even working with 3D point cloud camera data in a web browser was viewed as impossible. And by diving deep into the problem space, we figured out not only how to do it, but how to scale multi-sensor 3D labeling to any computer or network connection, opening up our workforce to anyone in the world. And in the demanding world AV field, we set the standard for data quality and precision. So we built our suite of annotation products like Scale's 3D Sensor Fusion and Scale Image to help drive the industry forward in working with complex data for just perception models. Our systems can go from 2D or 3D bounding boxes to panoptic segmentation in images to full scene 3D fused panoptic segmentation with cameras and radars, lidars, and all sorts of different sensors. And we do this by not by treating each sensor individually, but by working with the data simultaneously and providing interfaces that give people intuitive control over how they look at the scene. Mapping is inherently a sensor fusion problem. You need aerial or space-form data to understand where things are in the world and provide rough structure. You need street-level data to know what businesses are where. And since most companies don't have logos painted on their roof, you need multiple views of the same scene to give people context, and non-visual data to be able to answer questions like what hours is the store open or what services they're offering. Each company working with map data has some specific goal they're trying to achieve, and most require a custom point of view. And there might be a few perfect places in the world where images will give you all this information at once, but that's not true for the majority of the world. If you're going to work with multiple sensors, you have to be able to fuse them all together. It's not as simple as aligning satellite captures to the global coordinate system. And our product starts with the data itself. We spend a lot of time with you to understand your data, understand how it relates to each other, and what you're trying to achieve with each piece. Then our system automates fusing it together, and is constantly is asking for feedback and corrections from our workforce to create a flywheel, making the system better with each piece of data that we work with. And we have experience fusing really different things together, like SAR data with on-the-ground camera imagery. And the consistent goal of our tooling is to make sure that people are working with the data have as much context as possible at their fingertips. All of this led to the development of our latest product, Scale Mapping. While there's a few people providing maps, our customers consistently called out that relying on third-party GIS solutions results in data ownership issues, stale maps, or lack of customization. And at its core, mapping is still a data labeling problem. It requires high precision, scale, rapid turnaround. And for our customizable maps that embed semantically rich information that's relevant to your specific use case, that's where Scale shines. With Scale Mapping, you own your own maps, and the product is built to be easily customizable for your needs. We're one of the few companies in the world fusing multiple sensor data together at true production volumes. And as you can see in our work with Nuro, one of the leaders in the autonomous delivery space, we partnered with them early on to provide perception data for their system. And when they were ready to scale up and productionize their R2, we were the choice for annotating their map of the world. And it's running today in their delivery fleet. The data Scale provides lets the R2 ensure safe, accurate, and efficient autonomous delivery. And with that, I'll hand it over to Maria to talk about what her team has built out in more detail.
Thank you, Elliot. Hi, everyone. My name is Mar. I'm here to talk about why do you need HD maps and who may need them. The first use case is probably the one a lot of you came here for, is everyone who needs really, really detailed map data. So all of your AV, ADAS companies that rely on hyper accurate map to actually function. And no matter what they tell you, it's not mapless driving, it's just driving with less map, because even if they don't 100% rely on the map, you still need the map for routing, you need map for validation, you can use your map data for training your models, or as a prior for your perception, or as an input to your AV stack. But AV and robotics customers are not the only people who may need or may use the HD maps. Anyone who uses custom data layers in traditional maps may require something that you would call an HD map. So for example, industries like energy sector, insurance may want to add additional layers to the standard map, like power lines or water pipes or building damage or anything like that, and link it to a specific address. All of that would be an HD map. Or large logistic companies like UPS will not just rely on the business addresses and the point of interest, which is the centroid of the building, but more detailed building entrances and other information to actually figure out their deliveries. And last but not least, actually, route efficiency is a big part of HD maps, because you can't plan a very efficient route without understanding lane level information, which is basically what HD maps are. And basically, your navigation systems technically use HD maps if they tell you to turn left from the third lane or what have you. And then anything and everything like delivery and logistics, public transit, they all may require very explicit route information. So what are the current challenges with HD maps? The number one, Elliot sort of touched on that, is flexibility. You lack customization, you miss very important information that may not be tailored to your use case. You can't modify any of the map relationships. And then your core business basically relies on the map that's owned by somebody else. So any major changes to the data structure or lack of updates may cause a significant disruption to you, and any kind of feature prioritization is out of your hands. One very notable example, Google Maps was used and loved by everybody because they have pretty good standard of detail of the map. And then in 2017, they completely changed the pricing structure, and using that API became cost prohibitive for a majority of people, unless you're a huge company. So that's why relying on out of the box maps sometimes is really difficult. On the second hand, scalability when it comes to making your own map is a huge undertaking. You have to train a massive workforce. And while you can automate some of the mapping capabilities, there's a lot of things that are not super regulated. When we talk about construction, sign placement, a lot of it is still dependent on human judgment, and a lot of the map will not be automated away anytime soon. And mapping work is never done because maps rely on the real world, and the real world changes, you need to make updates. And that brings me to the last challenge with the maps, is iteration. The changes, as I said, are inevitable. You have to be able to detect them and address them as quickly as you possibly can to continue normal operation. And the more detailed your map is, the more debilitating these changes could be, but also it could take a lot longer to actually make them. And lastly, systems that use the map in whatever stack that you're using may change, may evolve, and therefore the requirements for your map may evolve. So you actually may need to change the map based on what your systems need on any particular time. And again, you kind of want access to that. How actually is Scale addressing that? Our approach is very similar and yet very different to what is considered the common industry practice. So we focus on flexibility overall. We offer you any types of input format. We support many data sources. We support custom taxonomy, and you basically can modify anything. Scalability, it's in our name. Scaling complex, labor-intensive tasks is what we do best. And mapping basically takes it to the absolutely next level. We have to develop a lot of proprietary training, instructions, workflows to be able to quickly ramp and down the mapping workforce. And that's actually a very crucial part there, because map changes are not predictable. So you never know what kind of demand that you have, but because we have access to large workforces, we'll be able to actually prioritize that. And last but not least, iteration. And the way we support this is our pipeline is very flexible. So it spans from change detection to 3D to 2D to mapping top-down annotations and all types of projections and different coordinate outputs. So you actually get lots of data from us that can be used, not just for traditional map applications, but in other things like training or other parts of your system. And the most important thing, again, Elliot touched on it a little bit, is you actually own your data. So we don't just send you a black box localization map solution. We send you your vector data and all of the relationships in the format that you need. So it never expires. You can change it. You could use it. You can prioritize updates to it however you like. So, and now we can basically go into a little bit more detail of like how we actually accomplish a lot of this, starting with flexibility, and it's all rooted into sensor fusion. We basically took our best learnings from annotating some of the most challenging 3D perception data sets and apply them to maps. We understand that accurate annotations require consistency across a variety of data sources. So in computer vision, like here, we use timestamps to associate the data because that's what usually makes sense. And then when we take it to mapping here, you can see this is a much more detailed point cloud. We actually use location to associate the data. But in terms of annotating, it's usually annotating stationary objects in 3D, like traffic signs, traffic lights. And as you can see here, and basically they're also still projected in cameras and a variety of views. So we can actually achieve really, really high accuracy annotations in 3D, assign them global attributes, and then also be able to project it in all of the cameras, as you see in here. And then mapping actually takes it a step further into a top-down task, because annotating maps in full 3D is not the most efficient way, and you have like a whole other dimension to make mistakes in. So this is an example of an actual mapping task. So we take in 3D annotations, ingest them into mapping, which is a top-down task, but we preserve all of the 3D information about relevant objects, so we can fuse sensors really efficiently. Talking about flexibility again, what happens if you don't actually have LiDAR sensors? We could use a variety of other inputs as long as they're georeferenced. Like for example, you could actually start with just regular map like OpenStreetMaps or satellite data and use georeference data to enrich it. Like for example, dash cam videos with like GPS information is something that you could use to enrich your map information here. And if you have really good calibrations, if you have GPS and new data, we're actually able to annotate in, for example, satellite view, and then project it into the camera views as closely as we possibly can. Obviously not really getting as close as LiDAR could get, but at least to some level there. And that's just like one example, but another example for more generic map use cases is user comments and feedback and stuff like that. So like, for example, this is a business change. So someone said, okay, this used to be a gym, now it's actually not a gym. How do we go into change it in the map? We can verify it in like a dashcam video if we have, confirm that actually, yeah, in fact, this is now a new business. We can go into the map, edit the point of interest, make sure it's all correct, and basically address that user report. And again, like we could use multiple user reports to verify each other, or use more trusted data sources like a dashcam or prioritized data sources to confirm that actually did happen. The last part of the flexibility is obviously offering you your own custom map. So how we break it down is starting with vector annotations. So basically annotating anything and everything that is visible to the human eye. So in ways that is suitable to your taxonomy. So like buildings, curbs, lane lines, crosswalks, sign lines, signs, traffic lights, all of that stuff that is visible in the map. We can absolutely add in whichever ways you would prefer. And then from that, we actually build on the vector maps layer and build a semantic map layer. So all of these things that you have a lot more flexibility to define, like lane centers, turns, parking areas, they're usually generated from these vector annotations. And yeah, like we work really closely with our customers to actually define how these operate and what they would be. And then you can assign a wide variety of attributes to all of these annotations that are 100% and completely custom to your specific use case. So like however you want to structure them, we figure out how to actually make it work with that tool. So as you can see here, like it could get really, really complex depending on what use case you're looking for. And if you have, again, multiple sensor type data types, we will be able to project them in all of your cameras and preserve all of the annotation information there as well. And then the last and probably the most complex part of our mapping annotations is semantic relationships. So all of that is also 100% user definable. So you could link things to each other. You could say set, for example, which traffic lights control which lanes, or actually specify like what is this lane behavior should be for that specific traffic light signal. You could link it to signs. You could link things to one another. You could actually define which lane needs to yield to what lane, stuff like that. Basically, the world is your limit. Yeah, this is probably our biggest IP. So I've talked about we offer scalability through access to our specialized massive workforce. We know that mapping is very labor intensive. And even with automation, we still require some human judgment in a lot of cases. It requires continuous updates. And so like we're actually really prepared for a variety of throughput depending on the needs. And the core capability here of us is actually instructions and workflows and understanding quality, because with maps, quality is extremely important, because when you're training your models, you could be 95% accurate, like you can have a 95% accurate data set and have it be useful with maps. Unfortunately, it's very categorical. Your map is either accurate or inaccurate. So the quality there is approaching 99 point something percent. And it's really difficult to do. So what we actually strive to do is break down the instructions and tasks in a very, very simple tasks that don't require like super high cognitive load. So we work with a lot of guided workflows and like step-by-step annotations. As mentioned before, like a lot of semantic annotations rely actually on base annotations, like vector things that already exist. So we try to pre-generate them as much as we can. We try to use ML assisted tooling to help our taskers. And ultimately, we also built a lot of tools to actually understand quality and understand how a specific person is performing and what they need to improve upon. So like we actually continuously check on how our workers are doing, and if they're like not performing to a specific quality standard, we send them training tasks mixed in with their actual tasks and also evaluation tasks as well. So yeah, so we basically handle all of your mapping operations there. Briefly touched on the pipeline. I think Stephen is going to talk more about that, but our pipeline is really flexible, and it starts with a single, you send us data once, but it goes through a variety of stages depending on what data you have or what data you need. So if you have lighter point cloud data, we take it into a 3D annotation stage where we annotate traffic lights and signs or anything else that needs to be actually in 3D. From that, we move on to top-down 2D annotations for most of the things, because it's a lot more efficient to just annotate tiles in top-down as opposed to having to do that frame by frame or in 3D. And we also do most of the linking in top-down. We import 3D annotations in there as well, with preserving all of the UIDs, so we can actually build relationship between 2D and 3D annotations. And then in the step after the annotating all of the 2D top-down annotations, we actually process all of the data and unprojected, because we preserve all the 3D information of the point cloud and in the world coordinates. So we can actually generate full 3D annotations out of the top-down annotations as well. And you get very rich outputs. So you don't just get one vector map, you get a vector map in world coordinates or whatever coordinates are your preference. Basically, this is sort of one of the things we focused on, that we are able to output in many different formats. But on top of that, you also get all of the camera and image coordinate projections for all of the annotations with all of the UUIDs preserved, and you have full 3D LiDAR coordinate annotations for all of your 3D annotations as well. So not only you get a map, you also get data sets for training and anything else you may want. And it's one-to-one UUID and vertex preservation. So you could be really versatile with how you use this data. And finally, what it basically allows us to do is actually basically have your map your way in very custom sort of way. So like, you own your map, you don't have to actually wait for us to update it. If you need to go in and change something in the map, it is absolutely possible. And this is what we strive for. And we should hand it off to Stephen, who will talk more about how we actually make this a reality.
Awesome. Thanks so much, Mar, for the product overview. Hey everyone, my name is Stephen, and I'll be doing the technical deep dive into sensor fusion. So on the next slide, you'll see that overall, there's two main sensors we're talking about today, camera and LiDAR. And if you're new to sensor fusion, I'll give a brief description of why we need both of them. So cameras, they excel at continuously capturing full color and high resolution images, and they're also comparatively cheap. Color in particular is extremely important to mapping, as you might have noticed in some of the videos Mar showed earlier. When you're looking at lane lines or signs, you really need color to get the full semantic accuracy, and these are important parts of any good HD map. LiDAR, on the other hand, it works similar to sonar. It shoots out light waves, and then when they return to the sensor, it can figure out how far away the object that was detected was. And this depth measurement enables LiDAR to precisely locate points in the 3D world. So for my section, I'm just going to give an overview of the 3 steps involved in our sensor fusion process. Sensor fusion here means we're combining camera and LiDAR to provide the richest labeling environment possible for our taskers. And hopefully by the end, you'll walk away with good understanding of the core concepts in sensor fusion. The first step is top-down vector annotation. What this basically means is we have a top-down tile like the one you see here, and it's been colorized in a way such that features like the crosswalk are clearly visible to the human eye. And you can notice that the red stripes here, they correspond to the high intensity parts of the crosswalk's paint. And that's allowed our tasker here to figure out where to put the box. The polylines and polygons that we produce here, we call them 2D vectors. They live in the image space, but if we're going to want to see them in the camera space, we're going to need to go to the 3D world. The way we go from 2D top down into 3D is using the ground mesh. The picture here is a visualization of a point cloud in 3D. In addition to the points being colored by intensity, we also render the green ground mesh, the large surface that's kind of spanning this entire picture. So the ground mesh, it's basically the surface which we expect all annotations to lie on. We're kind of exploiting the prior that things like crosswalks and lane lines, they're going to be on the same ground that we walk and drive on. So essentially, when a user is using our tool, they draw an annotation. Then behind the scenes, we're going to figure out where that annotation is in the world by kind of unprojecting and hydrating that Z coordinate. So again, what's the point of projecting into 3D? It's all for the sake of fusing LiDAR data with camera data. And if we turn to the next slide, you'll see what we can do with the world coordinates. So with world coordinates, we're able to determine exactly where a point might be in the camera image. So you've probably all experienced this before. imagine you're holding your phone, taking a selfie, and you're just kind of like positioning your head in a way to get that perfect shot. What you're doing there is actually just evaluating camera matrices on the fly in your head. You're trying to find the shot that puts your face maybe in the center of your image. And the math behind this is basically, if you know where a camera is and where it's pointing, you can perfectly model it and figure out where objects will be in its images. So that's what we've done here. We've taken annotations from 2D, projected them, unprojected them into 3D, and then reprojected them into camera images. These are the 3 steps that we do to make sensor fusion work. And it's what enables us to get both high geometric precision off of the LiDAR data, but also great semantic accuracy by using the color imagery. Next, I'm going to go into some of the algorithms that power these processes so that it's clear how it works. First, colorizing the orthographically projected tile. The high-level story here is we need to assign a color to every pixel of our tile. The way we determine that color is by looking at the intensity and elevation of the LiDAR points that correspond to that pixel. Every pixel of the tile image, it's actually an infinitely tall column in the real world, a tall column pointing, up and down. And we can easily find which points correspond to that column by just bucketing the points according to their X and Y. And then once we've extracted those points, we can take a statistical summary of the intensity and elevation and then encode it in the red and green channels of our image. That's the top-down tile generation process. Let me briefly cover the high-level techniques used to compute the ground mesh. If you recall, the ground mesh is necessary to be able to go from 2D into 3D. And it's computed by looking at the point cloud and analyzing it to find the surface that best fits the ground points. We first segment the point cloud into ground and non-ground. This will help us get rid of things like trees or poles that aren't actually on the ground. We also remove non-stationary objects in this phase. Then we compute a best fit surface, making sure that the surface is, mostly smooth. We don't want to have it have, high protrusions or like deep spikes into the ground due to possible noise that comes from the LiDAR sensor. Noise often arises if there's things like a puddle of water on the ground or a shiny object, because then light will reflect off it and travel farther than it's supposed to. So once we've computed the ground mesh, we serialize it, send it to our tool so that it can query it in real time when doing unprojection. And finally, I'll cover briefly the math behind the camera projection. As I mentioned before, the physics of a camera are pretty well understood. The pinhole camera model is what we use in optics to kind of figure out how the light will pass through the camera's lens and then be focused on its optical center. And we can fully parameterize this entire process using the camera matrix. The camera matrix is a linear transformation that encapsulates both the camera's extrinsics and intrinsics. If you haven't heard these terms before, that's okay. It just means extrinsics is the 3D pose of a camera. That's where is it located and where is it headed? What is it pointing at? The intrinsics of a camera, as you might have guessed, are its intrinsic properties. These properties don't really change as you move the camera around. For example, its zoom level, how wide or narrow its field of view is, and also basically the resolution of the images that it produces. What is that? Those count as the intrinsics. And then finally, if you've ever done computer vision on camera imagery, you'll know that lines become curves, and that's because of distortion. So as a final step, we need to rectify these images. There's a lot of standard algorithms for this in computer vision libraries. One such example is the Brown-Conradi model. It's just a formula that you slap on to your pixels to unwarp it. All the parameters here, they're just numbers. You can compute them ahead of time through a process called camera calibration. And they are what allow us to take an object in 3D and figure out where it would show up in 2D. That's it. That's all it takes to do sensor fusion. If you look at the next slide, you'll see our HD mapping product page. On this page, you'll actually be able to play around with it if you want to play with it yourself. You can see here that the camera image has all the projections from the annotations that were drawn in top down. This happened automatically. No, we did not manually draw the same things on the camera image and the top down tile. It was all done via the process I described of unprojection into the world and then reprojection into each individual camera image. I'll turn it back over to Hannah, who will run our Q&A session.
Great. Thank you so much, Stephen. All right, now we have some time for Q&A. So if you have any questions on what was presented, please go ahead and submit them using the Q&A feature in Zoom. Just to kick things off, first question I have is, how do you label traffic lights if they're not on the ground mesh?
That's a really good question. Traffic lights that aren't on the ground mesh, indeed, you don't want to label them from top down anyway, because you'd only be able to see kind of the top of the traffic light, which might not have all the information necessary, such as how many bulbs does it have, how are the bulbs oriented, is it a left turn or right turn traffic light. So we actually have a pre-annotation phase in our pipeline where we just use generic cuboids to label our off-ground objects. So we have a pipeline set up so that you first do things in 3D cuboids and then go to top-down annotation.
Great, thanks. The next question I have is, what are some common features of a map that are useful to semantically link?
I guess I could take this. I think it depends on what your use case is. For AV ADAS use cases is obviously linking lanes to a variety of things like traffic control devices. So traffic signs, traffic lights, each other, like can you change lanes from this lane to the other one, to crosswalks, other stuff. But I think lane is probably the main thing that is linked to other objects because it's the main thing that you interact with. And then for non-AV use case, things that we've seen is basically points of interest, like an address could be linked to a variety of things like a building, entrance, drop-off point, anything like that. So again, it all comes back to whatever use case you have. But with our pipeline, you can link anything to anything. Links are basically objects, like annotations in our annotations. So you can actually define what you want linked to what and how. And if your link actually needs to have an attribute, like for example, for lane changes, it's not just enough to link two lanes together. You also have to specify, well, with this link, can you go from lane A to lane B or not? And stuff like that.
Great. How do you handle stitching map tiles together to build out a full map?
Stitching map tiles together to build a full map, that is a very important step. It's what allows us to take a big problem like labeling all of America into a small problem, which is just labeling like maybe 300 by 300 meters. So the core concepts here are continuity of annotations and ensuring consistency in the linear geometries. So the way we do this is we ensure that when we annotate adjacent tiles, that we do it in a particular order, and we also seed the labeling tasks of adjacent tiles with the results from previous ones. So we add some padding to the tasks so they overlap, and then give a little tail of each annotation that might need to be extended so that the tasker working on it will know to preserve the continuity there.
Great. Are there any issues handling very large maps with lots of features over a wide area? Have you hit any issues with rendering that amount of elements in a web page?
So very large maps with a lot of features, we definitely encountered those. Our typical task can have anywhere from like 200 to thousands of annotations. So yes, the performance of our rendering engine is definitely a concern. Each of these annotations themselves might have dozens of vertices, and that can be, if you're not careful, very computationally expensive. We use a variety of technologies, including WebGL and SVG to render these. But the biggest strategy here is actually just some core concepts from UX. You don't want to overload the user with detail when they don't want it. So we follow those principles and hide unnecessary information from the user, which also definitely eases the load on their CPU and GPU.
Great. What can go wrong if a HD map is out of date?
A lot of things could go wrong. if HD map goes out of date. Like, for example, you may have experienced in your regular life, like when you're driving and your phone or whatever you use for navigation tells you, turn left onto Mission Street, and you're looking at the road and there's actually a big, huge no turn left sign. And obviously, as a person, you could make a decision to not do that because hopefully your neural net has been trained really well. But this is like a minor change. For self-driving cars. They may rely on the same thing a lot more, and they may or may not have a detection system that detects no left turn signs. So if they don't have it, they will actually try to turn, and that may become problematic. Same with your deliveries, for example. If your address is associated with a wrong building or wrong entrance, or sometimes in like rural areas, actual like mailboxes are very, very far away from the actual building address. Your packages may not be delivered. So there's a lot of issues that the out of date map can result in. For anyone living in San Francisco, a big example is Van Ness Street, when they're installing the bus lines in the middle, and it's been like 5 years late, and mostly it's because all of the infrastructure underneath the Van Ness Street, they don't know what's there, so they actually have to do exploratory digging before they can actually do any work. And if they had maps that wouldn't be out of date, that probably would have been a lot faster.
Great. Have you ever worked without LiDAR? For example, video, photo, GPS, Axel?
So we've definitely labeled just raw camera imagery, drawing the lane lines, but as you might imagine, that data without depth information is going to be hard to consume and port to other sensors. GPS information is really bad if you're driving in big cities. And even when it's good, it's not going to be accurate to the centimeter level precision that HD maps need. The same goes for onboard IMUs. Those will tell you a lot about the car's localization, but you really need good LiDAR data to get the highest quality like SLAM algorithm outputs.
Great, thank you so much. So that's all we have time for today. For next steps, we'll be sending you an email with the recording. Please let us know what you thought of our talk. The survey link should be in the chat. And Elliot, Amar, and Stephen, thank you so much for your time today. And thank you everybody for joining us. Have a great day.